All right, so as you can see, I said this earlier, I have whited out my title and written something else underneath or up top. And that's because my title was boring, said something about sampling distributions, and then I changed it to backward stack magic because it just made me much happier. So today I'm going to teach you about backward stack magic, and it's basically what helps you estimate things that are real off of your lazy samples. So remember, we talked yesterday about how to be lazy and just take a few samples and then use that information to figure out stuff about the population. That's what STACT is. If you could walk out of this class and somebody be like, what is that class about? You should say, being really lazy and taking a few samples and using that information to estimate something about a big group that you don't know anything about. And if I could break this whole class in one sentence, that's what it would be. And it's cool because I'm lazy. So I like to see how it actually works, and I can use my laziness to make even good decisions. So we're going to use most of the stuff from yesterday. So we don't have a lot to write today. It's actually only one side of a piece of paper. I know. But we are going to go back to the two things we did yesterday and talk about those also. So fortunately, there's not a lot of writing. You can give your hands a break today. But okay. So when I say backward stack magic, that's one of Mrs. Talbot's goofy things that I say that actually has a real vocab word, which is unbiased estimator. So unbiased estimator means what is safe to use. What is safe? What statistics are safe to estimate the original population from? Because believe it or not, they're not all safe. So we're going to investigate the two that we did yesterday, the brothers one and the M&M's one, and see what is safe. Okay. So first thing we're going to do is define unbiased estimator. And this is unfortunately has some writing. Where's my pen? I don't know if you saw, but there was a conglomeration of teachers in here earlier. And okay. Okay. Unbiased estimator. I'm hoping this makes sense to you. A statistic. Okay, so thinking about a statistic being an estimator because that's what you got from your sample. So remember, sample starts with S, statistic starts with S. Those two things go together, sample, statistic. A statistic we use to estimate, that's the whole point. Okay, and I'm just going to go something like mean, median, IQR, proportion, dot, 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 any of those things that we can calculate. Where the mean, and I'm going to put in parentheses center because this is kind of a visual exercise of its sampling distribution is equal to the population parameter. Okay, there's a bunch of words there, and it's 8:41 in the morning, and I probably lost you, so I'm going to go translate this as a teenager or Mrs. Talbot when she was learning it many years ago. Okay, I want you to think of this more of a visual thing than a bunch of words. What I'm saying is, if I take a bunch of samples and I make that sampling distribution dot plot dealio, and I look at the middle of it, because the middle of it is really what you're going to say would be your best estimate, right? If the middle of it is equal to what the true thing should have been, if you're looking at it and the middle of it is, right about where you think it should be, then it's an unbiased estimator and it's safe to use. Okay, I want you to think about yesterday with the M&Ms we did. think about that dot plot we made. Was the center of that dot plot about 0.25? Yeah. So that means it's a safe to use. Unfortunately, they're not all safe to use. You can't really do it with all of them. So we're going to look at mean and range because those are the two that we did with the brother situation yesterday. So the first thing we need to do is figure out the actual mean from the four brothers. Okay, so we're going to start with mean. And I'm going to use some real vocab here so that you guys I'm not using all of Mrs. Talbot fun words. Do you guys know what the symbol is for the population parameter for the mean? It's a Greek letter. It sounds like a kitty cat. Mu, right. Okay, so if I had asked you to yesterday, this was our stuff from yesterday. If I had said, ignore all of this stuff, and back up to here, focus on this. Could you find me the population mean? Could you have found me the population mean in July? Could you have found me the population mean in 7th grade? Yes, you add the four numbers and divide by 4. That's what I mean by finding the population mean. You guys know how to average things in 7th grade? No? 8th grade? Yeah. Oh, I meant as children, if you walked into my class as 7th graders, little adorable stats kids, like all of you, I'm just picturing you in your little middle school days, and you came in with your little notebook and your little calculator, and I said, could you average the numbers 71, 75, 72, and 68? Could you do it? Okay, that's what I'm asking. Okay. Yeah. And the reason I'm saying that like that is because I'm using all these fancy words. I'm using population parameter, I'm using mu. All I'm asking you to do though is add the four numbers and divide by 4. Okay, so coming back over here, 75, 71, 75, 72, and 68. The population parameter is 71.5 inches. Okay. Now, I would be a bad teacher if I didn't pause right here and tell you, can you always find the population parameter? Do you always have all the information? No. Why? Because this is a contrived example I made up so that you could do the thing. Very easy numbers and stuff to just practice. But most of the time, you're not going to have that. That's the beauty of backwards stats magic, because you can kind of figure it out. Okay, now go back to your graph of the mean sampling distribution from yesterday. So flip your paper back. And I want you to find for me 71.5, which is the actual mean. Is that the center of my dot plot? You see the beauty of such a simple example. It's like perfectly symmetric. I could fold on that line. It would perfectly line up. Yes, it is the center of that dot plot. Okay. Again, it's only because we got the exact, it's very satisfying. We got the exact thing, but again, it's only because we have the tiny population and stuff that we make. But what does that mean for us? That means that we can estimate the population mean from the sample means. We can use backward stats magic with the mean. The mean is safe to use. Okay. I'm gonna show you some more examples of this, but we're gonna write this out. And then I'm gonna have you watch me do some stuff on an applet, which is totally not gonna be boring. You're totally not gonna fall asleep. You're totally gonna watch and you're gonna be totally engaged in my applet and it's gonna be wonderful. I promise. I can't promise that. Okay, but this is my discovery. X bar can estimate mu, which means the sample means can estimate the population mean. That's supposed to say sampling. I don't know what happened. Okay, now this is one of those things that once you figure it out one time, you don't really need to figure it out every time. So I know I gave you a very small example, very small stuff. I'm going to give you some more examples. But after this, you guys should be solid in the fact that mean is okay. You can use sample means to estimate a population mean, which is great because mean is the most, would you guys say that is the most common statistic that we use? So it's good to know that that's safe to use. Okay, so now we're going to do range. You can make this closer if you want to. I just wanted it to be spaced apart. Okay. Now, as I said yesterday, unfortunately, there's no fancy symbol for range. You have to just put range. I don't know if you guys like the fancy symbols or not. I like them because I'm lazy and want to write less, but they might be confusing. Okay. This is a 7th grade question. How would I find the range of the population? And let me help you. I know it's a 7th grade question, but we got a lot of stuff written here. Okay, let me narrow it down for you because I love you. Okay, here you go. Only look at this. How would I find the population range?
Biggest number minus small number.
Next. Okay, I know it seems simple, but we got a lot going on here. I don't want to go too fast. Okay, so biggest number is 75, smallest number 68. Okay, now 7. Flip back to your range dot plot from yesterday and find 7 for me. The big vocab question, I'm gonna ask you a common sense question. Meaning, if you just had this dot plot yesterday and these numbers yesterday, what would you have estimated the population range to be if you didn't know? Take a look at your dot take a look at your ranges. Common sense, complete total, like critical thinking, common sense, looking at the dot plot, looking at the ranges, what would you have estimated the population range to be? What would be your best guess? 3 or 4, three-ish, 4-ish? Right, because this is kind of where the bulk of the graph is located right here. Kind of the middle-ish of the situation, we have 1 at the 7. Okay, would you have said 7? No. Okay, so what I'm saying is, you can't use sample ranges to estimate the population range. Unfortunately, range, not safe to use. So we will not be making sampling distributions of range after today, because they're not good. Why would you do it? Because they're not helpful. They're not gonna help you figure out the range. So. And why do you think that is? I think it's probably because of the subtraction bit. Anyway. Okay, now, I don't know if I would have thought about it when I was in high school, but when I was in college, I would have sat in a lecture like this and I would have said, holy cannoli pants, there's a lot of different statistics I could calculate. Do I need to go through every single one of those and figure out which one is I can use to estimate? And the answer is negatory on that, because we're gonna focus on 2 main ones. So you guys do not need to go through your entire list of statistics to figure out whether they're biased or unbiased. Mean is great. Range, I mean, how often do we use range anyway? And I always told you range was terrible because it had all the outliers and stuff in it. So this really shouldn't be that surprising. After you guys write this little bit here, I'm gonna ask you to relax and watch me work with mean and range a little bit more on my applet. And you're definitely going to like say stuff and you're going to nod at me and give me eye contact. Like you're definitely following along in class and you're not going to fall asleep in my applet because I'm doing it and you're not. And you're definitely going to be like, wow, my hand is taking a break right now. I'm so grateful for that. Okay. So I prepared for you before you got here. This applet is, oh, I don't know if that was bad. Okay, anyway. I prepared this for you before you got here. And I just made it really skewed on purpose. Okay, so I want you to pretend that these are, so this is 0, 1, 2, 3, 4, they go by ones up to 32. It's a very skewed population of numbers. A lot of small numbers, not very many big numbers. Imagine it's something like incomes or something, where it's like a lot of people make small amounts of money and only a few people make a lot of money. And Mrs. Talbot from the small one, just kidding. Trying to wake you. Try real hard. Do I need to do a that shuffle? Is it working? Okay. So what I'm gonna do is I'm gonna take out a sample of 5 from this big amount of data. and it's gonna plot me the mean of the five, and it's gonna plot me the range of the five. Okay, so watch, it's gonna be exciting. If you could just make some sort of excitement sound, that'd be great. Okay. Ooh, this is so good. Okay, so it took out the sample of five, and it calculated the average of those five numbers. And then it took out another sample of five, and it calculated the range of those five numbers. Can you already see there's kind of a problem going on here? Okay, and since we've already discussed it, you can sort of tell what's gonna happen. Okay, so there's your sample, there's another mean. There's your sample, there's another, oh, now I'm like, I look like a liar. Okay, hold on. Ah, I look not like a liar now. Can you guys see the little red marks underneath where it's giving you the center? So can you tell this center's pretty on and this center's pretty off? That's kind of what I'm hoping you're gonna see here. Ooh, really off. Okay, now I'm gonna do something exciting. I'm gonna hit the 10,000 button. Okay, so it did 10,000 random samples of size five. Do you remember yesterday how I said the best way to do a sampling distribution is actually by simulation and not by taking actual physical samples? This is what I meant. It's just the computer can just do it so good. Okay, well, what do you notice? You notice that the center of the mean graph is pretty much right on. And that's what I'm trying to tell you. The mean is safe to use. You can use the center of that mean graph to predict the population mean, even if it's really skewed. Notice the shape too. What happened to the shape? It became normal. I just told that. That's foreshadowing for later. Okay, and then ranges. Okay, not only is it like completely off, it's really, really spread out, so it's completely unuseful. Okay, are you guys good there? Okay, now I'm gonna switch applets to talk about the M&M situation. Okay, so I want you to find your resource page from yesterday. Your dot plot at the bottom. Okay. By the way, real quick, even those ones that I did with the 10,000, those were not sampling distributions. They were still approximate. This 10,000 just wasn't all of them. That's why the computer's better. Okay, now, looking with today's eyes at yesterday's work, do you feel like sample proportion is an unbiased estimator of the population proportion? Oh, hi. Do you feel like, and what I'm saying in teenage words is, do you feel like you could have looked at that yesterday and sort of concluded that maybe the blooms were about 0.2 or 0.25 fish? Yesterday, would you have, like, you didn't know, let's say you had not had any of the information, you just said, oh, let's look at all these samples, blues, probably somewhere in this vicinity. Okay, so are you feeling confident enough to say that P hat might be an okay estimator of P? Do you know what those symbols are that I just said? Okay. All right, so I went to, now I told you guys, I taught this class out of two books, and I don't love the CPM text, but I steal things because I'm a robber. And I stole, I know, how could you, Mr. Sabat? I stole their proportion sampling distribution simulator. Okay, And I changed this to be our M&M situation from yesterday, so sample sizes of 20 M&Ms in your Dixie cup. True proportion of success was 0.25. Do you think you're actually gonna know that ever? No, that's the whole point of backwards stats magic. And I drew 24 samples because that was the class amount from yesterday. Okay, this is not exactly your graph. Why not? Why is it not? What, this is terrible. This isn't the graph we got. What kind of craziness is this? Why not? Why didn't I get the same graph? Yes, because of sampling variability, which means that every sample is gonna be different. So every time you take a set of 24, and that's why it's never really the exact sampling distribution because of sampling variability, unless you can do the entire list of all possible, which, the M&Ms, not possible. Okay, but it looks pretty good. Okay, so my question is, if you got this graph, would you be feeling like 0.25 is an okay? Okay, let me do it again. With, instead of 24 samples, let me draw 500 samples. Okay, how are you feeling about 0.25 now? Pretty good. Okay, so in this class, can we agree that mean is safe to use and p hat is safe to use? So X bar can estimate the population mean and p hat can estimate p. And if I can convince you of that, then we can continue with the rest of the year, because if we don't agree on that, then we can't do anything else. Okay, there's one more thing I need to teach you, and then I'm done, actually. I know, Mrs. Talbot. Okay. Back to this. Later that day. Okay. Now, let's say that you were in charge of estimating the proportion of the United States that was zombies. Okay, zombies, flesh eating, scary, trying to wake you up again. Flesh eating, scary. Not like slow zombies. I'm talking about the I Am Legend style zombies. Do you know about I Am Legend? The Will Smith movie? Okay, I have a story. My husband took me to see this movie many years ago, previous husband. He didn't know, not his fault. It was anniversary date. And I had only seen the commercials on TV where it appeared to be a drama. All I saw was Will Smith in the streets and there was like a lion. And I was like, that's cool. Let's go see that movie. That sounds great. And then when we got there, I realized that it was actually an extremely triggering horror film. I hid under his leather jacket for 2 hours, asking him to take me home. And he just kept saying, this is so cool. Anyway, true story. And I got like weirdly into it. Like I had to read the book and stuff. I was so freaked out by the whole situation. Anyway, zombies. Okay, zombies. Okay, so the reason I'm saying zombies is because I want you to think that this is Life or Death. All right. So you're in a lab. You're in a movie. You're like, okay, Mrs. Talbot taught me stats, right? So I want to estimate the population that is zombies right now. Do you want to estimate that off of a very spread out graph? Or would you like to estimate that off of a tight graph? I'm asking. Would you like to base that life and death estimate off of a graph that's spread out this wide? Or one that's like about, here with a small curve? Do you know what I'm saying? Wouldn't it be better if your data was closer together? Wouldn't that give you a better estimate to save everyone's life? And then you could be Will Smith yourself, and then I'll do the 0. Okay. So smaller variability is better. What I mean is, if you can have numbers that are closer together, much easier to make your estimates. What is the biggest influence on the variability, do you think? Maybe from what I wrote there. From what I wrote there in the second line. Sample size. Okay, sample size is going to be the thing that gives you the best estimate. And what do you think, just from common sense? Larger or smaller sample size better? Right. Then you're done with the notebook. Then I'm going to show you one more exciting applet situation. And then for my math people in the room, I'm going to explain why this makes sense mathematically. So I have 2 more things to do, but after this, you're actually done writing, which is nice. Okay. Okay, so I'm going to go back to this. Skewed population, right? Numbers 0 through 32. A lot of lower numbers, not very many higher numbers, and you're definitely still going to pay attention because I'm definitely not done. Okay, and what I'm going to do for you is I'm going to take sample of size 5 animated again. It's going to find the mean of that and plot it here. Then it's going to clear this and take a sample of size 20 and put the mean of that here. So it's going to take 2 samples, one of size 5, one of size 20. I'm going to do the animated thing a couple of times, and then I'm going to hit the 10,000 and we'll see what really happens. Okay, so first, okay, so there's your average for 5. There's your average for 20. Notice how close those are. And notice how close those are to the original. How comfortable do you feel about means? You should feel pretty good about it. I'm going to do this one more time, just so you get the gist of it. Okay. You guys all understand what's happened so far. Okay, and it's not that exciting at the moment, but I just wanted you to know what was happening before I hit the 10,000 button. Okay, and this is what I was trying to express to you about sample size. So if you're trying to estimate, I don't know how you would do average zombies, that's not really a thing. Average. It's still proportion, it doesn't matter, it's fine. My zombie thing was flawed, but trying to make this as fun as humanly possible. So pretty dead on with the population mean, but still kind of spread out. So if that's all you've got, you know, you're like, oh, well, this is clearly the center, but you know, there's a lot going on. This guy, sample size of 20, dead on, and also your numbers are much more tight, so you can give a better estimate. You can feel much more confident in saying that. Do you see what I'm saying? Okay, so, and as the sample size goes up, this is one of those like calculus things, it gets tighter and tighter and tighter, so it approaches a perfect normal curve. Okay. Last thing, I promise. Okay, let me show you my, this is for my math people in the room. And I have math people. And I want to show them this. Okay, so please don't look at the giant one at the bottom, just look at the top one. So this should not be that. This is what we learned today. The mean of all of the sample proportions, so the middle of the sample proportion graph, should be equal to the population proportion. So the middle of that 0.25-ish was 0.25, I'd say. So this is the center of the dot plot was 0.25. Okay, this is the standard deviation over here, which I'm going to teach you in later lessons, don't worry about it. But I want you to notice n is in the denominator. Okay, and what happens when the denominator gets bigger? What happens when the denominator of a fraction gets bigger? Fraction gets smaller, which means that your variability gets smaller, which is why that graph got shrunk up smaller. Okay, I'm going to show you the same thing for means. This is, if you're a visual person, you might hate this. If you're a math person, this will appeal to you. Okay, again, means. The center of the dot plot of means is supposed to be the mean. Standard deviation, n is in the denominator. As n increases, variability decreases. That's mathematically why you got a tighter curve than the other one, because there's formulas. Guess when we get to learn the formulas? It's definitely tomorrow.